Welcome back to our discussion of multi-junction solar cells. In the previous video we looked at the spectral utilization of multi-junction devices and the JV curves of single junctions with absorber layers of varying bandgap energies. We will now continue our discussion by looking at how different junctions in a multi-junction are electrically connected. We therefore look at the equivalent circuit of a semiconductor junction. As discussed in the first course of the solar energy program, IPH represents the photo-generated current density, while ID represents the dark current density or saturation current density. Each junction in a multi-junction device can be represented by a single equivalent circuit. This means that the junctions could, theoretically, be connected in series, or they could be connected in parallel. We can gather from the figure that the parallel connection requires electrodes between each of the layers. However, generally, the junctions in a multi-junction device are stacked onto each other and are therefore connected in series. This means that the voltages of the individual cells add up in the triple junction cell. So if we look at the JV curve of the triple junction device, we can see that its VOC is approximately equal to the combined VOC of the three triple junctions. Furthermore, the current density in a series connection is the same throughout the entire solar cell, which means the current density of the triple junction is determined by the p-n junction generating the lowest current. Finally, we look at the band diagram of a triple junction device. The top cell with the high band gap is shown on the left hand side and the bottom cell is shown on the right hand side. This band diagram does not represent reality, however. If we were to place three p-n junctions in series, the p layer of the top cell and the n layer of the middle cell, for instance, would form a p-n junction themselves. This p-n junction would operate in the reverse direction with respect to the single junction solar cells and would therefore significantly lower the voltage of the triple junction device. To prevent this from happening, so-called tunneling junctions are included. These tunnel junctions align the valence band at one side with the conduction band at the other side of the tunnel junction. The tunnel junction has a very high band gap energy to prevent parasitic absorption and are relatively thin with an extremely narrow depletion zone. As a result, the slopes of the valence and conduction bands are so steep that the electrons from the n layer can tunnel through the small barrier to the p layer, where they recombine with the holes. It is important that the tunnel junctions have a low resistance to minimize the voltage loss across them. In a triple junction cell, two tunnel junctions are present. The first is located between the top and the middle cell, and the second between the middle and the bottom cell. Electrons and holes are generated in each of the junctions. As explained in the first course of this program, electrons move down the conduction band edge, while holes move up the valence band edge. Consequently, the electrons generated in the top cell, here indicated on the left, are collected at the front of the device. Holes generated in the bottom cell are collected at the back side of the device. The holes generated in the top cell and the electrons of the middle cell recombine at the first tunnel recombination junction. The holes of the middle cell and the electrons of the bottom cell recombine at the second tunneling junction. Indeed, in this series connected type of multi-junction solar cells, only the minority charge carriers of the top and bottom cell are used to power a load in an external circuit. These series connected multi-junction cells are also referred to as two-terminal multi-junctions and are the conventional configuration for multi-junctions. Some more exotic device architectures include 3 or 4 terminals, but these architectures are not very common. More information about 4-terminal multi-junction devices can be found in the second course of our MicroMasters program on solar energy engineering. In summary, we have discussed how using multiple junctions in a solar cell can increase the spectral utilization of a device by decreasing the amount of excess energy. We saw that the junction with the highest bandgap energy always acts as the top cell and that the junctions in a multi-junction device are connected in series. Consequently, the voltages of the individual junctions in a multi-junction configuration add up, and the current of the device is limited by that of the lowest generating junction. Finally, we discussed how the multi-junction devices require the use of tunnel recombination junctions. In the next video, we will discuss a challenge for creating high-efficiency multi-junction devices, namely current matching.